Hey everyone, in this video, I'm going to give you a brief overview of the E3 software and what are all the parameters that you need to find, to model an airplane in the simulator, right? In this video, I'm going to talk about these four categories that you need to find data for: the CG and mass parameters, fuselage, propulsion, undercarriage. I'll talk about the H and V panels and like control mappings in the next video. Okay, so uh, the first and foremost thing, you have to assign a coordinate system for the aircraft, because everything that you're gonna do, the way the wings and the tails are positioned, the aero center information, basically the way it goes into the sim is with respect to the datum or with respect to the origin, right? So I mean, a simulator does have a capability to basically change the origin anywhere you want, but um, we strongly recommend that you put the nose at the 0, 0, 0. So basically define that as an origin. Another thing that you have to keep in mind is the way the sign convention is imposed in the sim software, right? So X, again, on this side is positive. Again, to the X to the right is to the left is positive, right? Z to the bottom is positive, and Y to the top is positive. All right. So you got the side view and the top view, and which shows basically all the sign conventions that you need. So just know when you are defining the aero centers of the wing and the tails, make sure to use the right sign conventions associated with the coordinate system. Otherwise, your model will be seriously wrong. Okay, so just keep that in mind moving forward. It's very, very important. Okay, so now let's jump into CG and mass parameters. So when you go to the model editor, this is the tab that you'll see, and these are the information that you're actually going to get. All right. So right away, what I have in this red box means to leave the values as it is in the example file. Now you don't have to change anything. All right. But the values which are not highlighted is where you have to find the right values for the airplane and feed it in. All right, starting with the aircraft mass, so put the empty mass. The one thing, the simulator only accepts values in SI units, right? So if you're working with English, you have to convert everything to SI units, okay, or metric. So you got the empty mass, you put it in here, and it's very important to also kind of estimate where the CG of the aircraft will be, and again make sure that you have the right sign conventions when you are putting the CG location in here, right? And that's it. This is the aircraft empty mass, and then you have the payload mass is different in the different category, right? So if you are general aviation airplane, you can change, you just put the weight of the, you can put the payload weight of the passengers and baggages, in this category right here, right? So the initial mass and final mass is the same. The reason why there's like different masses because you can use definitely can program the airplane to drop a mass like a firebomber or like a cargo airplane like dropping ammunitions or like um, and other things midair. So you can definitely ask the simulator to model that. But since we're not doing any high performance or esoteric airplanes, just you can keep the initial final mass the same, right? And here you basically have the initial and final locations of your payload. So if you're not changing the payload, then just have it the same, right? This is basically the center point of where the payload will be, right? So the coordinate system where you actually put the payload on the aircraft, right? So you're gonna have to like find that and then put those coordinates in here, right? Since you're not dropping anything, well, you don't necessarily need to deploy and the reload time. You can just set that equal to 0. So just click initially load it and make sure to uncheck this box, otherwise you'll be dropping passengers, right? Don't do that. Um, so yeah, and keep in mind, again, please keep in mind the aircraft axes, the sign conventions, what is positive, what is negative, and all that. Okay, so that's pretty much it for the CG and mass parameters. Oh, fuel, I forgot about fuel. Well, you have to find the fuel capacity of the aircraft and then put it in here. And this is basically the CG location of the fuel. So again, you can assume symmetry. Right, so most likely the CG of the fuel lies in the fuselage, right? But you can estimate the X and the Z location to be like a mid-span 40% chord like location, right? So that kind of gives you a good idea of the CG location of the fuel. Well, I guess the midspan doesn't make much sense. You are if the wing is swept, then yes, in a midspan 40% chord location is a good approximation. Okay, if you have a Hershey bar wing, then just a 40% chord location would be a good estimate for the CG location of the fuel. Okay, that's pretty much it for the CG and mass parameters. Let's move on to fuselage, right? So the fuselage, you don't have as many parameters as before. It's just you're gonna find the aero center of the fuselage. Again, I hope by now you guys know what a aerodynamic center is. If not, please look it up. Okay, at this point you should know what an aerodynamic center is. Right, so you got the aero center for the fuselage. A good approximation is the center of the fuselage or a little ahead of the center of the fuselage is maybe a good approximation. And the reference area here is a minimum cross-section area of the fuselage when looking at head-on. Okay, so make sure to estimate what that minimum cross-section area will be and then put that in here. Well, you got to know the fuselage length, right? So along with, you have to know where the pilot sits, the pilot's eye position, so that when you enter and sit in the simulator, you kind of seeing something realistic as you would see on an airplane that you're modeling. All right, so again, it's very important here. One thing that you can leave it as it is the drag coefficient. Um, it really depends on like what type of aircraft that you're modeling. If you're modeling general aviation, then whatever the values that are already entered here should suffice. But if you're doing some slender wing type like aircraft, slender wing fuselage, um, well, if you're modeling airplane which has a slender fuselage, then you may need to change few parameters in here. But for now, just keep it as it is, whatever the values that are already in the example file. But again, keep in mind in the aircraft that you're going to design, you're gonna use some of the equations that we're gonna talk about to actually estimate the drag coefficient of the fuselage at different alphas, different angles of attack, and also at different yaw angles as well. And here on the right, you have the Mach CD rise. So basically what this means is that as you're approaching transonic speeds, you're gonna have like shock waves appear in the fuselage, and when that happens, the drag basically goes up, and that's basically what you're trying to model in here, right? So Mach number of the CD or the DCD, which is change in CD, but I'm sure none of you are going to model the high performance or transonic airplanes in this stage, but you should definitely, and you can definitely think about modeling a transonic like a commercial airliner, um, like for your aircraft design for this course, right? And that you have to account for the Mach CD rise as well. But it's a very simple equation that you can use to model it, so it's not that hard. So all right, so that's basically it for the fuselage. And then, don't worry about the air brake. If you have spoilers, then, then basically you have the air brake. Let's ignore the air brake for now and just jump into propulsion. Okay. So propulsion is basically where you input the engine performance parametrics and engine like geometry and locations. So, first and foremost, you gotta select the engine type, right? You gotta see whether the aircraft has a piston prop or a jet engine, what kind of jet engine, turboprop, or turbojet, turbofan, or something else, right? And then select number of engines. Time constant is basically the response time. Once you push the throttle in the simulator, how long does it take for the engine to pull up? So that's basically 0.8 seconds. You can just leave it as it is. If the aircraft that you're modeling has a jet engine, then you can reduce it further too, which is kind of this doesn't matter that much. It's just to get some realistic feel for the aircraft or for the model, right? So, but if you're going with general aviation like a Piper or something like that, then definitely some Pipers have a pitch wing, but some Piper aircraft may have a variable like pitch prop. So you can definitely choose whether or not just check the spots if the aircraft has a fixed pitch, but uncheck it if it has a variable pitch. Right. So So then you put the engine power, the prop diameter, max prop efficiency, prop design speed, and all of that in here. This you should be able to find online for the aircraft that you're looking at. The specific fuel consumption, again, that you should be able to find that as well. The things that you can ignore for now are the windmill drag, the P effect, the torque, the gyroscopic effect, wash effect, the prop wash linear, prop wash wall, all that effect, you can basically ignore. But when you're designing the aircraft and putting your design in the model, then you have to think about how to estimate all of these as well, right? So this tab, this section is only for a piston prop or turboprop, but you have a jet engine, then you basically put it in here, right? The parameters, the sea level thrust from the specific fuel consumption, all that in here, right? So no matter what type of engine you have, you're gonna have to specify where the engine is mounted, right? The X and Y locations of the engine, and whether or not it has any yaw or pitch angle. Most likely it should not have any yaw angle, hopefully, unless I think there may have some airplanes with the yaw angle, but depending on like what type of aircraft you choose, even like some general aviation aircraft have some pitch to the engine mount locations. Okay, so that's pretty much it. And you can ignore this custom the thrust lapse table for now. We can talk about that later when you're designing the airplane and whether or not you actually need it. All right, so here that's pretty much everything for the propulsion, and then we'll move on to the undercarriage. The undercarriage is basically the landing gears. Okay, um, so hold on. That should be over here. I'm just editing this as we go. All right, I'll explain what those are in a minute. But basically, like, you got the main landing gear, right? Track is basically the distance between the two, like main landing gears, right? You put that in there, and then the X coordinates, Z coordinates of the main landing gear, right? If you have multiple landing gears, multiple main landing gears, then just pick a center point. So basically, you're looking at the center point, okay, of the main landing gears and putting it in here. You can leave the stiffness and damping as it is, but for the airplane that you're going to design, you're going to have to find a good approximation for these values. But for now, just leave it as it is. Preload is basically, the estimate of how much load is acting on the main landing gear. A good approximation is 75% on the main landing gear and 25% on the nose landing gear. But again, that's a good approximation. It may not be what it is in, for the aircraft that you're designing. So there are airplanes without any nose gear, right? So in that case, well, 100% is basically acting on the main gear, right? So for now, just estimate like the 75% on the main gear, 25% on the nose gear, right? 75% of the overall weight, right? So, and then same for the nose gear, you get X coordinate this and a minus 0.8. Well, this is just an example, right? But you can just specify the mid location of the nose gear in this field right here, and we already talked about the preload. So brakes, well, just keep it as constant. You don't need to change anything else. But again, for your design, you have to play around with this data. Now, this is very important right here, the nose wheel steering. So when you're on the ground and you're taxiing to the runway, well, it's important, the way you taxi is by using the rudder pedals, okay? So when you press the pedals when you're on the ground, you're not activating the rudder, you're actually basically steering the nose wheel, right? So this 15 degrees is basically the range of motion of the nose wheel it's allowed to turn. 15 degrees is a good approximation, just leave it as it is, right? But the authority table is something that you really need to know, all right? So what this is that, as the airplane is gaining speed, at some point, the aircraft will get off the ground, right? So when it gets off the ground, you need to transfer the authority of the pedals from like changing the nose wheel to changing the rudder, okay? Does it make sense? Because since you're using rudder pedals, it's even in real life you use the rudder pedals to taxi the aircraft to the runway. But once you're airborne, the nose wheel doesn't respond to the rudder pedals anymore. You basically, the rudder will be affected by the rudder pedals, right? But there's you gotta put the transition in here. So look at this, like at a speed of 0, right? There's no aircraft speed. The authority is basically all the way like 100%, which means that if you have 0 speed, then you have like 100% authority on the nose gear, right? 10 knots, well, you reduce about 75%. 20 knots about 50%. 30 knots about 25%. About 40 knots for the aircraft that is modeled in this example. 40 knots is like the rotation speed. That's when you basically rotate the aircraft. You gain enough kinetic energy that you basically rotate the aircraft so that the nose gear basically comes off the ground. And when that happens, the authority basically goes to 0, and your full control pedal authority basically is used to change the rudder, the tail. All right. So in order to do this, you really need to know what's the rotation speed, or you can estimate the rotation speed of the aircraft and set your authority that way. Okay. Does that make sense? Hope that makes sense. All right. So that's pretty much it for this video. In the next video, I'll talk about the H panels and the V panels. Well, you don't have to worry about systems or tuning. We'll talk about diagnostics later. But the important aspects in the next video that will be covered are the H panels, V panels, and the control mappings. Right. That's where you basically model the wings and the tail. So far, we model the weight, the fuselage, the engines, and then the landing gear. So what's left again is the wings and the tails, right? So that we'll cover in the H and V mounts, and I'll show you what to do in this different panel, in the different tabs as well. All right. I'll see you guys in the next video.